My name is Lydia. I will be monitoring the chat. So if you do have any questions, please either ask in the chat box and I can relay them, or alternatively, you can unmute yourself. These are interactive conversations. So we're happy to take questions as we go.
Yeah, I have a whole deck of slides that I could get through, or we could not. We could go off on unrelated tangents and I could answer a bunch of questions. Yeah, no one's complaining. Cool. All right. Well, let's get going. So for those of you I have not met yet, I'm Dr. Selander. I'm geology faculty here at Highline, and I'm going to be talking on tangentially related to geology because it has to do with the Earth and where we live. But we're going to focus today on extreme weather events. This is something that we hear a lot about in the media. Like if we think back like 5, 10, 15 years, watching the news during the summer or the fall or any time of year, weather never really made like the top stories in the news. And now it's really hard to go even a week without hearing about some extreme weather event somewhere in the world. And that's not just because they're getting more coverage, it's because these extreme events are happening more often as our global climate is changing. So what I thought we'd do today is not so much focus on climate change and global climate change, because we've done a lot of talks on that, and the science on that is pretty settled. What I'd rather do is focus on the science behind these extreme weather events and what produces them. There we go. So as a quick outline, if we get to all this, great. If we don't, great. What I thought we'd cover is we'll start by defining what weather is, because we kind of use those terms weather and climate a lot in our common conversation, but it's really good to know the distinctions between the two, because there's a really big difference between those two terms and what they mean. And then really what do we mean by an extreme weather event? I will talk about some examples and then go into really the background science behind what causes these events. And then talk as we kind of go through, talk about impacts on various populations, not only human populations, but some of the biologic populations as well, because these extreme events affect really every living thing on our planet. So weather, we can kind of think of that as stepping outside. So if we were to leave this room, go outside, what would we experience? So Manveer, what did we experience about half an hour ago when we went outside? Yeah, it was raining. Yeah, so we just in a class, we went outside to make some measurements and it was raining. That's a perfect example of weather. It's like, what are the conditions in the atmosphere at a specific location at a specific time? And depending on kind of the granularity of your weather app, these conditions can change like hour to hour, minute to minute in some places. So there's that kind of that common phrase like springtime in the Pacific Northwest. If you don't like the weather, wait 5 minutes. And if you still don't like it, wait another 5, and then you'll be fine. So that's weather. Things like rain, sun, wind, cloud cover, all that stuff that we can go outside and observe at a specific time. So kind of a good way to think of weather is you wake up in the morning, check the weather forecast, and you decide, what am I going to wear? Do I need to bring a rain jacket? Do I need to bring sandals? Do I need to bring sunscreen? Do I need to bring all of it? So that's our weather. And weather is influenced by a number of different things, primarily season. Here in the Pacific Northwest, we're lucky enough to live in a part of the world where we experience 4 very distinct seasons that have their own very distinct weather patterns. Other kind of smaller scale things that affect weather, things like changing barometric pressure. Low pressure here generally means that we're going to have rain, high pressure, sunshine. And then when that pressure is changing, we get a change in our weather. Wind direction, convergence and divergence. This can affect weather on a very local scale. If you're from this area, quick poll of hands. The convergence zone. Heard that term in the news? Maybe. Next time you're listening to the weather forecast, especially on the local news, pay attention for the term convergence zone. And what's happening there is you have wind coming in off the Pacific Ocean, kind of at surface level, splitting around the Olympic Mountains, and then converging on the other side, generally over kind of the Seattle Everett area. And where those winds converge, there's really nowhere for that air to go but straight up. And when air goes up, it generally produces clouds and storms. So at some point this spring, what's kind of fun is to stand on the Highline campus, be in beautiful blue sunshine, staring out at the Puget Sound and the Salish Sea, and then looking north to Seattle and seeing these giant dark storm clouds. That's the convergence zone. So that's an example of how local wind and topography influences weather. So that's kind of our daily weather, stuff that we're used to. But extreme weather is when we get, for lack of a better term, extreme conditions or unusually severe weather conditions. And these can be devastating on ecosystems, human populations, biological populations. Historically, in the past, these had a low probability of occurrence. So based on like a 10-year record, an extreme weather event would happen once every 10 years on average. So it's saying like if we consider a flood an extreme event, a quote 10-year flood would be a flood that has a chance of happening once every 10 years. So annually, there'd be a 10% chance that flood could happen. So that's one way to define them is statistically. Another way is we call impact-related thresholds. How big are these events? How severe are they? So things like when we have rapidly increased rainfall intensity, or the number of consecutive days of really, really hot, or on the opposite end of the thermometer, really, really cold weather. And these are also location dependent. So as an example of location dependent extreme weather, let's go back to June, July of 2021. Who was here then? Yeah, it was warm. It's unusually warm. In fact, record warm. There's this map that we have here shows the temperature anomaly. So this is one thing that we use when we're describing conditions either in the atmosphere or temperature in the oceans. We use what we call a temperature anomaly, and that's the deviation of the measured temperature from a long-term average. So over that period in late June, early July of 2021, temperatures in the Pacific Northwest were anywhere from about this red 10 to the dark red 15 degrees Celsius warmer than average. Celsius, we're used to thinking in Fahrenheit. So 10 to 15 degrees Celsius warmer, that's anywhere from about 12 to over 30 degrees Fahrenheit warmer than the average temperature. Sustained highs were around 40 degrees Celsius in some places. Just kind of as if your brain doesn't really think in Celsius, 37 is your body temperature. So that's extremely hot weather. And this is sustained for 4 to 5, in some cases, weeks of this extremely hot weather. So in our part of the world, yes, that's an extreme weather event. If we were to go down to Arizona, say Phoenix, and there were weeks where it was 40 degrees Celsius, 105 degrees Fahrenheit, that's their normal temperature. So this is what we mean by location dependent for extreme events. So you have to think about where we are and what the average conditions in the past have been and what they are during these extreme events. So thinking a little bit more about that 2021 event, it's such a great example. This graph is showing daily maximum temperatures in the Seattle area between January and December, so all year, between 1979 and 2021. So each dot on that graph represents a single day and the high temperature for that day. So as we'd expect, cooler in the winter, warmer in the summer, cools off in the fall. Let's throw in that 2021 event. Let's draw a line on there showing the average, and then let's throw on 2021. There's a June 26, 27, 28 in 2021. Well above average, even beyond some of the warmest temperatures ever recorded in this area. So that's your extreme event. So in July of 2023, just this past summer, we had significantly more days above 80 degrees for high temperatures. So that's showing this kind of increased occurrence of these extreme hot events in this part of the world. This heat wave, not only did it break records for temperatures, but also huge impacts of that. So over 600 deaths were related between, or reported due to heat-related illnesses or problems between Washington, Oregon, and British Columbia. There were rapidly spreading and increasing wildfires during this heat event because things got so hot and they dried out. In fact, the town of Lytton, British Columbia, which is about there, recorded the highest daytime temperature ever in Canada, about 45 degrees Celsius. The next day, the town was gone, burned. So these are very extreme events. And then it wasn't just people. There's a massive die-off of billions of marine organisms, especially ones that live in the intertidal zone between high and low tide. So during low tide, those organisms are exposed to the atmosphere. Normally used to the cool maritime climate and temperate climate of British Columbia and the Pacific Northwest. But you expose those same organisms to sustained like days and weeks of heat that's 10 to 15 degrees Celsius warmer than average, those organisms dry out and they die. So this really impacted not only shellfish, but all the creatures that depend on them for their food. So there's this massive die-off of marine organisms that corresponded with this heat wave. Of course, extreme weather events don't just happen here in North America. 2023 in Libya, Northern Africa, Storm Daniel dropped about 16.3 inches of rain in 24 hours. That's roughly twice what Libya gets in a year in the course of a day. Combine that with 70 to 80 km/h winds, you get massive flooding, over 4,000 dead and tens of thousands missing and displaced afterwards. Back in North America, back in February 2021, the quote unquote Texas freeze, where temperatures in the Seattle area were about 20 degrees warmer than they were the southern tip of Texas. This is caused by a giant displacement of Arctic air turned to polar vortex. I'll explain that in a little bit more detail in a minute. But this caused tens of millions of people to lose power because the Texas power grid was not set up to handle this extreme cold. And there were over 200 weather-related fatalities during this event. And back to the West Coast, California. Intense flooding during this past winter 23 to 24. Large events termed atmospheric rivers. An atmospheric river is not a new term. We'll talk about those in a little bit, but they are getting more and more intense. They're getting more and more wet. There's a lot more moisture involved, meaning they can drop a lot more rain and a lot more snow. So you can simultaneously have in the Los Angeles area, you could have at the same time surf watch or surf advisory for large waves along the coast. You can have flash flood warnings in Los Angeles. And then you go up into the hills and the mountains just outside Los Angeles and you have avalanche and blizzard warnings. You don't really think blizzard and avalanche warning when you think Los Angeles. No, these are pretty extreme events. And then one more example, Europe in 2022. There were areas in Europe where the sustained daily temperature was 20 degrees Fahrenheit, about 10 degrees Celsius warmer than average. This was responsible for approximately 25,000 deaths due to heat-related illnesses and other problems. So these extreme events, they're kind of symptoms of what's happening globally with our climate. So as global average temperatures are rising, the occurrence of these extreme events is also going up. So we can ask, Why? What's the relationship between adding to our global average temperature and these extreme events? What is the correlation there? So just as another side note, we don't have 2024 data because we're still early in that year, but 2023 was the warmest year on record, kind of by far. This is another graph showing the temperature anomaly with reference to an average global surface temperature between 1901 and 2000. 2023 was about 1.2 degrees Celsius warmer than that average. And that's the highest recorded global surface temperature anomaly so far.
So when do we update what average is? Like right now, it's showing from as far back as 1880 all the way up to 2023. But at what point do we say that what happened in the late 1800s is no longer normal on this planet?
That is a
And
good
we
question.
raise the average and say, now this is what the normal average is.
That is a good question. I do not know. I do not know when the average will be updated. Primarily because most of the models and data right now is referenced to either a 1950 to 2000 or a 1900 to 2000 average, because this is about when instrumental records got really, really good. And then, around 1980 is when temperature started going up. So, real quick, greenhouse effect. You add gases like carbon dioxide, methane, even water vapor into the atmosphere, they trap more heat. As the atmosphere traps more heat, temperature goes up. Real quick greenhouse effect. I'm not going to go into the exact chemistry and physics of it. But big takeaway, more greenhouse gases in the atmosphere, more increase in temperature. All right, so the primary greenhouse gas that we are concerned about and that we use to judge a lot or to measure a lot of these things is carbon dioxide. So I forgot to check just now, but in October 23, carbon dioxide was at about 418, 419 parts per million. So for every million molecules in the atmosphere, over 400 of those are carbon dioxide. And the reason why that's concerning is that if we look at the geologic record and go back 800,000 years, between 800,000 years ago and about 1911, the carbon dioxide concentration in the atmosphere was never higher than 300 parts per million. And now we're well over 400. Yay, humans, we did that. Yeah, just the rapid increase is what's alarming. There were times in the geologic past where, yes, global carbon dioxide concentrations in the atmosphere were higher than they are today, but the average global climate was much, much different. And it took thousands to millions of years for that concentration to change, not the 120 years that it's been for a rapid increase of over 100 parts per million. So what this does is we have increased greenhouse gases in the atmosphere. Again, due to human activity, we're increasing the amount of heat trapped in the atmosphere. So we have to ask, what's heat? We use these terms so much. We use heat and temperature. Do we ever really stop and define what we mean by those? Like we touch something and it's hot. Ooh, yeah, it's got a lot of heat. Or we measure our temperature and say, ooh, something's a high temperature. We're running a high temperature. We have a fever. So let's think about those two. So temperature is a measure of the average amount of kinetic energy in the molecules in a substance. So kinetic energy, again, it's the energy of motion. So the more a molecule is moving around, kind of if you think of a solid, the more the individual molecules in it are vibrating, the more temperature it will have, or the higher temperature. Heat is a transfer of energy from one object to another, and due to their differences in temperature. So can I grab a volunteer? Anybody? Yeah, come on up. So just as an example, so if you just like kind of held your hand out anywhere, you kind of feel the like the temperature of the room. So what you're also feeling, you're also feeling a little bit of heat. So the atmosphere in this room, full of molecules, those molecules are flying around. And when they're bouncing off your skin, they're transferring a little bit of energy into you. And so you're feeling essentially the heat of the room by the temperature in your hand. So put your hand right about there. Oh, what's different? Very warm. Yeah. So what this lamp is doing, our heat lamp, is it is exciting the molecules in the atmosphere, giving them a whole lot more energy. So there's some reaction going on in the bulb. And what it's doing is it's transferring a bunch of energy from the bulb, from electrical energy, into energy of the molecules in the atmosphere surrounding the bulb. So they're a lot more energetic. They're moving faster. And then when you put your hand underneath it, those faster moving molecules are hitting your hand. And so you feel that transfer of kinetic energy from the molecules in your atmosphere into you.
Is it the same with everybody?
Yeah. Same with everybody. Yeah. Yeah, so you put your hand here. Yeah, woo, yeah, same thing, still warm. Yeah, so that's our heat and temperature. So what happens is as we increase the temperature of something, density decreases. So density is, again, a measure of how much stuff or how much matter is in an object per unit volume. So as we heat something up, as we add temperature to it, as we add energy to that object, the volume goes up. So you can imagine being in a crowded room where everybody's standing still. Not a whole lot of energy, and you can compact a lot of people into a small space. But then imagine everybody starts flailing their arms and jumping around. What happens? You're going to spread out to get away from the crazy guys that are jumping around and flailing their arms. So the amount of volume and space you're taking up is going to increase. So, oh yeah, that's still on. So if our water was boiling by now, we could do it. We'd see the water expanding in volume and actually going into the atmosphere as it expands, as it heats up, as its temperature increases. All right. So along with heat is a concept of heat capacity. So this is going to be really important when we start talking about some of these drivers for extreme weather events. So heat capacity is the amount of heat, the transfer of energy needed to raise the temperature of an object. And if we want to get into the nitty-gritty, it's how much heat is needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So just for a couple examples, water has an incredibly high heat capacity, which means we can add a whole lot of energy to water before it starts increasing in temperature. So what water has the ability to absorb a huge amount of energy before its temperature actually increases. Things like sand or iron or metal, they have a fairly low heat capacity. As soon as you start adding energy to them, their temperature goes up. So that's why you go outside on a very hot day, you walk into a parking lot that's paved and it's super hot because it doesn't take a whole lot of increase in energy transfer to get that substance, that pavement to start heating up. So keep this in mind right here. So water has a very high heat capacity. Again, that means we can add a whole bunch of energy to water before its temperature starts going up. So just kind of an example of that. Got a quick little demonstration. Hopefully this will work. If it doesn't, I'm about to get very wet. Okay, everybody see just the plain old candle that I've got going? All right. So I got a couple balloons with just regular old latex balloons. So the melting point of latex is about 120 degrees Celsius. So if I were to place just this empty balloon over this candle, there's not a whole lot of energy this balloon can absorb before it starts to melt. Not much at all, right away.
Let's make it go that
Yeah, I wasn't expecting it to go that fast either.
quick. Forget the
But
balloon.
usually it takes like a second, usually it takes a second or two. That was
They ain't gonna help.
I'm done. All right, so let's do the same thing again. But this time, just in case, I don't want.
The candle in the box.
Yeah, just in case. I mean, physics says this should work. This balloon is full of water. So if this experiment will work, I should be able to put this balloon right on the water, or full of water right in the candle. Nothing happens. Just get a little burn mark in the balloon. Yeah, that's because the
water in it?
Yeah, exactly. The water is absorbing the heat from the candle.
Yeah.
Yeah. I'm not gonna keep trying that until it pops.
I feel like we put the balloon into the thing just in case that weak spot on that latex.
Yeah.
There we go. Yeah, just in case.
Leave that there. Okay. So the heat capacity of the water in there is super high. So all the heat from the candle, even though it's just a little bit, it was enough to pop the empty balloon, or the balloon is full of air. But when you add water to it, that water starts absorbing the heat, and not all of it goes into the latex. So there's one other heat-related concept, and that's called latent heat. And that's the amount of water, or the amount of heat that's absorbed or released during phase changes. So as, let's say water goes from solid to liquid. It requires heat absorption to go from a solid to a liquid, because as a solid, all the molecules in water are stuck in a rigid structure. As it goes to a liquid, those molecules need a little bit more kinetic energy to start moving around. And then you need to add even more energy to it to get those kind of the hydrogen bonds between the individual molecules to break and actually turn that water into a vapor. So there's a latent heat of melting and a latent heat of vaporization, where water needs to absorb heat in order to go from a solid to a liquid and a liquid to a gas. We can also go the opposite way. As water vapor cools down and goes from a vapor to a liquid, it gives off heat into the environment. As water goes from a liquid to a solid, it's also giving off heat. It's giving off energy. All those molecules go from moving around a whole bunch to being stuck in place. So again, going back to our intro physics classes, we can't really create or destroy energy. It just gets transferred from one form to another. So all the energy from our liquid water goes into the atmosphere as it goes from liquid to solid. And then the opposite way, as our water goes from solid to liquid, it takes that energy back out of the atmosphere to add to the individual molecules. So we just did that. So the other thing, let's talk about circulation. So we've got a little bit of knowledge about water and heat. So the other thing, you need to think about the atmosphere. So our normal atmospheric circulation is driven by a couple things. Temperature differences between the equator and the poles, and the Earth's rotation. The end. I'm not going to get too detailed into all this stuff. So the main takeaways: temperature differences between the equator and the poles, and the Earth is spinning, no matter what you might see in some weird channels on YouTube. And that gives us circulation of the atmosphere. As the atmosphere circulates, we get a couple really fast-moving belts of air. One of them near the polar regions, and the other one in subtropical regions, generally approximately about 60 degrees north latitude and 30 degrees north latitude, and then same in the southern hemisphere. So anything that I talk about in the northern hemisphere, just swap it, and it's the same for the southern hemisphere as well. And these incredibly fast-moving belts of air, these are our jet streams. We have our polar jet stream, which generally separates very cold air in the polar regions from warmer air in the mid-latitudes, and our subtropical jet that separates the warmer air in the mid-latitudes from really warm air in the tropical latitudes. So our polar jet stream is really, really fast. I mean, these winds are moving anywhere from about 100 to 150 miles an hour on average. So this is a little visualization of motion in the upper atmosphere. The colors are scaled by speed. So we have our polar jet stream here moving in kind of these really warm colors showing it's moving very, very fast. And this narrow belt of really fast moving air is created by the convergence of very cold Arctic air masses and really warm subtropical air masses. It essentially kind of creates a wall in between them and separates them. And the reason why it's not just like a straight belt around the poles is this has to do with different atmospheric high and low pressure systems, so various weather systems. So where we have kind of a bend upwards north, we have clockwise rotation or a high pressure system. Where the jet stream bends toward the south, we have counterclockwise rotation or a low pressure system. What's been happening is as we've been adding heat to the atmosphere, again, due to increased greenhouse gases trapping more heat, the temperature difference between our polar air masses and the subtropical air masses has been decreasing. As that temperature difference decreases, what happens is the jet stream starts to slow down. As it slows down, it's more susceptible to those atmospheric high and low pressure systems, and it gets much, much more wavy. And what that leads to is our friend the polar vortex. So the polar vortex is, it's not a new term. This term and phenomenon has been around for tens of thousands of years. Okay, the phenomenon has, the term maybe is a little bit newer than that. But a polar vortex really just refers to strong winds and very cold air masses in the polar regions. Normally, when you have a strong polar jet, it contains that really cold air mass to the Arctic region. So we don't generally get really cold air in southern latitudes like down where we are. As you decrease the speed of the polar jet stream, because you're warming up the atmosphere here, warming up the atmosphere even more in the polar regions, the jet stream starts to wiggle and swerve a little bit more, and it can detach those large polar air masses, and it makes it a lot easier for them to move south. So we can think of our polar jet stream as a kind of a conveyor belt that will deliver incredibly cold air to the south as the polar jet slows down in its speed. But also, as it delivers incredibly cold air south, these big northerly swings in the polar jet can deliver incredibly warm air north. So we have kind of this double whammy where you have really cold air moving south, right next to really warm air moving north. And especially right along this boundary here where you have really cold air meeting really warm air, that's where we get a lot of extreme weather events. A couple examples. This is what the jet stream looked like in February of 2021. We had that really cold snap in Texas. We had this huge mass of polar air, difference in average temperature in degrees Fahrenheit, 45 degrees below average. So we have this big blob of cold air detached from the polar region, moved south. As it moved south, it also created space in the polar regions for some incredibly warm air. So you have this blob of cold air with the polar vortex moving south and really warm air on the opposite side moving up to the north. So when this was happening, we had areas around the Hudson Bay in northern Canada that were, 80 degrees Fahrenheit warmer than places in Texas. Ugh. So this can produce extreme cold events. This is another example just from this past summer, or past winter, excuse me. We have incredibly cold air descending down through the middle of the continent, incredibly warm air. So we had, at the same time, record low temperatures in central part of North America and record high temperatures in the southeast part of the United States. And in some places, as this jet stream, this polar vortex move from west to east, the temperature changes in places like Tennessee and Kentucky. Even over the course of a few hours, temperatures changed by 50 degrees Fahrenheit. Went from like 75, 80 degrees one afternoon. That evening, it's 30 degrees. And so this is one type of extreme weather event, these extreme and rapid changes in temperature. Other things, I'm just going to briefly mention this, but those where the polar jet allows really warm air to creep north, that's termed an omega block, because the shape of the jet stream kind of looks like the Greek letter omega, and it traps incredibly warm air in it, which is one thing that happened here back in 21. So because we're having this increase in heat in the atmosphere and our destabilized jet stream, we're having a really big increase in the frequency of these extreme weather events, especially extreme heat events and extreme cold events. And these really have different impacts on different communities. And for a minute, we'll think about primarily extreme heat events. Let's think about cities. Most cities are paved. There's a lot of artificial surface that's been constructed. What happens is that those artificial surfaces are really good at absorbing heat during the day and then slowly radiating it back into the atmosphere overnight. And what we call that is a heat island. It's areas that remain artificially hot after the sun is set. So after the source of heat on that object has gone away, it remains artificially hot. I actually got a pretty good demonstration up here. So I'm basically going to create an urban heat island. I've got 2 heat lamps. There's 2 things that are being heated up. One is a slab of rock. We can just imagine that as being some urban environment. And the other is just a bunch of moss and vegetation I grabbed from outside a couple hours ago. So they've been heating up, and we can use a thermometer, take their temperature. Let's see, okay, our rock is about 74 degrees Celsius. Pretty warm. How about our moss? Anyone want to guess what the temperature of the moss is in Celsius? So this is 74. Close. 50.
So I just did a conversion for those folks who don't think in Celsius. That's 74 degrees Celsius is 165 degrees Fahrenheit. You do not want to.
If anyone's curious, just come up and touch this.
And the other one was 50 degrees?
Yeah.
50 degrees Celsius is 122 degrees Fahrenheit.
All right, so let's do this.
Either way, less hot.
Let's do this. Imagine it's nighttime. Heat source goes away. All right, so we don't forget this. So we have our urban environment with the heat on it. That was what, 170.
74, I think.
Oh yeah, that's in Celsius. That's a pretty big jump.
165. Yeah.
Green.
Green stuff.
Yeah, that was
50, and that's 122 Fahrenheit.
okay. So those are the temperatures when I turn those things off. When I turn off the heat lamp. So we'll come back to that in a few minutes. So the heat islands are a huge problem in urban areas. And just as an example, Seattle. This is a map of evening temperatures. Again, going back to our 2021 heat wave. Evening temperatures between 7 and 8 p.m. So normally, sun's getting a little bit lower in the sky. We're not heating up the ground quite as much. The angle of incidence of the incoming radiation is a lot lower. But you can notice areas like between Auburn, Kent, Tukwila, what's right here? The airport, Boeing Field, Renton, a lot of those areas that are highly developed and industrialized and commercialized, their evening temperatures were still close to 100 degrees Fahrenheit. Compare that to areas like the Red and Highlands or out near kind of like Lake Young's or near Black Diamond, where you have a lot more vegetation. Their evening temperatures were about 76. So a 20-degree Fahrenheit temperature difference between urban areas and that have much less green space and more kind of suburban areas that have a lot more vegetation that's preserved. That is a huge difference in temperature. This is where 80% of the population lives. Areas that are considerably warmer. Even on our Highline campus, green cover or tree cover and green space, that can really help mitigate that urban heat island effect. And if you haven't been down there, we have an entire forest on campus. Over that way a little bit, past the parking lot. It's our own dedicated green space. This all belongs to Highline College. So one kind of fun thing to do if you're here this summer or even spring, because we'll probably have a couple warm days before the quarter's over, just walk across campus and just feel how the temperature changes as you're walking from a paved area, maybe across the track and then down into the forest and the green space. There'll be a huge decrease in temperature. Of course, it's not only extreme heat events, there's also extreme cold events. So it's easier to think of how heat events are really devastating to populations, but also extreme cold events. So let's turn our attention a little bit to the oceans. So the main driver for processes in the atmosphere, aside from atmospheric circulation, is the oceans. All the water vapor in our atmosphere that produces rain or snow or clouds or a lot of our weather systems comes from the oceans. So let's think back to heat capacity. And it's been a few minutes, you've probably forgotten what that is. So again, it's how much energy it takes for a substance to increase in temperature. Because water has a high heat capacity, water can absorb a whole lot of energy before it starts increasing in temperature. So when we are observing a temperature anomaly map for the sea surface, so again, this is looking at the sea surface temperature, deviation from a long-term average. I'd forget the exact average on this one, so let's call it 1900 to 2000. Areas that are in yellow and orange and red have a sea surface temperature that is anywhere from 2 to 5 degrees Celsius warmer than the average. Just last summer, there were areas near Florida where the sea surface temperature was warmer than your body temperature. So you normally think you're at the beach, yeah, I'm gonna go jump in the water and cool off. Jump in the water there some points last summer and you would warm up. So for this amount of ocean water to start increasing in temperature by 3 to 5 degrees Celsius or about 6 to 10 degrees Fahrenheit, imagine how much energy the oceans have had to absorb, how much heat energy. So this is one thing that's kind of alarming when we think of long-term human-induced climate change, is that we're looking at the temperature increase in the atmosphere, which is alarming, but so much excess energy that we put into the atmosphere has been absorbed by the oceans. So now we're starting to see this increase in sea surface temperature. And what that does is it increases how much water can be evaporated. So as water gains more energy, the molecules are moving around a little bit more, a little bit faster. It takes less additional energy to get them to go from being liquid to water vapor. And what happens to water vapor in the atmosphere? We form clouds. And if we have a bunch of excess water vapor in the atmosphere, we can form very, very devastating extreme storm events. This is a satellite image from one of the atmospheric rivers that impacted California last winter. This whole band of clouds right here, going from the Hawaiian Islands all the way across the Eastern Pacific to California. That's what we call our atmospheric river. So it's a narrow band in the atmosphere that contains an excess amount of water vapor in terms of clouds and just the overall amount of moisture present in the atmosphere. And when this very narrow, fast-moving belt of excess water in the atmosphere hits the continent, it rains out, or it precipitates out as rain or snow. And that's where we get these really, really extreme events. So atmospheric river, not new. The term is not new. It's been around for decades and describes these narrow bands of concentrated moisture in the atmosphere. Another term for this, especially when the air mass that the atmospheric originates from is kind of near Hawaii, Pineapple Express. So we generally associate Pineapple Express here in the Pacific Northwest with a period of pretty warm air temperatures and lots of rain. So been around a while. What's happening though, as we increase the sea surface temperature, we increase in evaporation. As we increase evaporation, we get greater and more intense precipitation on land, which greatly increase the risk of flooding and every other precipitation-related possible hazard. Extreme snow, blizzards, avalanches, floods, flash floods. A couple examples from California. Entire communities flooded. Parts of the whole Central Valley of California that used to be a giant lake before it was all cultivated for agriculture became a lake again. A huge, huge impact on populations, especially lower income and more marginalized communities that could only afford to live in floodplains. A lot of these communities were previously protected by levees, but those do not always hold up in extreme flood events, as we found out not only in California last year, but as Hurricane Katrina taught us incredibly well. Levees do not always work if they're not maintained, and especially if we have a huge amount of water.
We got a question in the chat.
Yeah.
Asking, are El Nino and La Nina caused by atmospheric river?
They are not. But what El Nino and La Nina can do is increase the amount of moisture available in the atmosphere. So that's actually a great thing to talk about. Let me go back to here. Because I'm almost done there. Ooh, forgot about this. Remind me to get back to our urban heat island after I talk about El Nino and La Nina. So El Nino and La Nina is part of this broader circulation pattern in the Pacific Ocean basin called the El Nino Southern Oscillation. And it happens when a blob of warm water kind of sloshes back and forth in the equatorial latitudes in the Pacific Ocean. So an El Nino is when there's an abnormally large amount of warm water in the Eastern Pacific. And what that can do is add a whole bunch of moisture to the atmosphere in this particular area. So it can increase the severity of storms that form here. It can also alter circulation patterns in the Northern Pacific. So this past winter, we were in a fairly strong El Nino. And as a result of that, we had a very dry, kind of unseasonably warm winter. Whereas a little bit further south in California, they'll be playing in the snow until July. They had a very wet, cold winter. La Nina is the exact opposite when we get a blob of abnormally cold water in the Eastern Pacific. And that can also alter circulation patterns, not only in the Northern Pacific basin, but also along the Western Pacific as well. So atmospheric rivers aren't necessarily influencing El Nino and La Nina. It's kind of the other way around. We can have an El Nino greatly influencing the severity of precipitation and the amount of precipitation that happens in these atmospheric river events. Great question.
Can we measure the temperature of your?
Oh yeah, let's do that. I don't know how long it's been, but okay. Evening. Who else wants to measure this? I don't want to measure this. All right. Urban. 54 Celsius. That's still hot.
Like 129 degrees.
Yeah, so
Fahrenheit?
about 129. So it's dropped. It's dropped a bit. It's dropped, 30, 35 degrees Fahrenheit. Green. 29. Almost half.
82.
Yeah, 82. So considerably cooler. That's our urban heat island right there, where you have urban stuff that's built up and paved, holding onto that heat and radiating it very slowly, versus green space that will absorb the heat, and then as soon as the source of heat is gone, the heat is gone. Yep. Oh yeah, kind of depending on where you aim in here. There's areas that are 25 degrees Celsius and areas that are 30 degrees Celsius. Heat has decreased quite dramatically. All right, so, perfect timing. So where I want to end up. So kind of a good way to summarize all this and think about these extreme weather events. Think of it as a cascading sort of thing, where we add more and more greenhouse gases into our atmosphere, which accelerates the greenhouse effect, or the trapping of heat in the atmosphere. That rapidly warms the Arctic regions, which changes the temperature gradient between the polar regions and subtropical regions, which slows down the polar jet stream, which leads to more extreme heat and extreme cold events, as that jet stream wobbles a lot more. At the same time, our oceans are absorbing a whole lot more heat. So even though the global average temperature is going up, the amount of heat the oceans are absorbing is massive. And then we've come to the point where we are greatly increasing sea surface temperatures, as the oceans have absorbed enough heat to start increasing in temperature, which leads to increased evaporation, which can give us rapidly intensifying hurricanes and typhoons and cyclones, kind of depending where you are in the world, how you name those storms. Now there are storms that go from a tropical storm with sustained winds less than 74 miles an hour to a category 4 or 5 hurricane in less than a day, which is crazy. It used to take weeks. And also greater precipitation in our rainfall and snow events. So these atmospheric rivers contain a lot more moisture in them. So there's a lot more rain and snowfall that can happen.
So when there's greater precipitation and rainfall, would that be thunderstorms or just heavy?
All the above. All the above. Yeah. Probably if there's a lot more instability in the atmosphere and you get a lot more vertical motion, then you'll get more thunderstorms. Other times you'll just get a deluge of rain. Yeah. Yeah, I hate to give a scary talk, but hey, now you know the science behind what's happening. That is Mount Rainier. That is Mount Rainier in the summer of 21, after it lost a huge amount of snow in about 3 days. Yeah. Yeah. Doesn't look like Mount Rainier. I'm like, wait, is that? I thought there used to be snow there.
We have to be worried about floods with all the snow coming on? Anything like that because of the snow melting?
This year, unless we get a really, really warm period over a warm couple days, not something to worry about this year because the snowpack is pretty thin at this point. Yeah, if we had what happened in 21, we had a really cold winter with a huge amount of snowfall, and then it melted off so fast, and that did cause a lot of flooding.
There's another question in the chat. It's two parts. Would it be true that while the US and Canadian weather is more influenced by the North Polar Jet Stream, South America weather would be primarily influenced by the Southern Polar Jet Stream? And is one of those jet streams stronger than the other?
Oh, part one, yes. So everything I said about the Northern Hemisphere and the polar jet stream, replace Northern polar jet with Southern polar jet, and it's all the same. Like you're still warming up, and there's a lot more swing in temperature. The severity, that I'm not sure, because there is that really big difference between the North Pole and the South Pole, and it's the existence of a whole continent at the South Pole. So there's not as much water there. I know Antarctica still is heating up quite a bit, but I haven't recently looked at the surface temperature anomaly there. I should look that up. That's good.
Do the jet streams travel at the same speed? Plus or minus?
Plus or minus.
Back during the pandemic, I did almost drive to the flying range, airport, really office. Have studies been done on whether that had a big effect on whether
There is a little dip in atmospheric CO2. Yeah, that coincided with when we stopped driving and going places.
You know about the Salton Sea in California? I thought it was shrinking.
When it does have water input, like especially this year, it will have a lot of water in it. Yeah, so this year, yeah, especially Southern California, like the Salton Sea, Death Valley area, received just an intense amount of rain. So people were out paddleboarding in Death Valley. And there are lakes in Death Valley that existed for a couple months. And then areas like the Salton Sea collects water from almost all of that part of Southern California, the Anza Borrego near Joshua Tree, that will all drain into the Salton Sea. So it probably has a lot of extra water in it right now.
And about the Great Lakes. That they losing water.
That I don't know. I know they've had a much lower precipitation than average in the upper Midwest this year. So there's probably gonna be less water draining into the Great Lakes this year. And those do tend to lose a lot of water through evaporation. But normally there's such a huge area feeding them that.
Well, somebody told me that we'd be getting, California would get more weather like us. But not necessarily we get more sunny. It sounds like the air is going to be rainy.
Yeah, so probably what's going to happen is California will continue to get these extreme events. We will also continue to get extreme events. But what's going to happen over time is the extreme events that we get, especially during the winter, will be more rainfall than snow events, just because the air masses that are moving over will be warmer. We'll have a warmer average temperature. So we'll still have winter. We'll still have big storms, but a lot more precipitation will fall as rain and less as snow, which can greatly increase flooding hazard. Because if you take the same amount of precipitation, spread it out over 4 months, and have a bunch of it fall as snow, let's say at elevations above 2,500, 3,000 feet, that can melt off slowly all spring. But if you take that same amount of precipitation, combine it into 3 really intense rainfall events, and we're flooding everywhere.
We have a couple more comments in the chat. One says, this is from Pam, who says, I'll admit most of what I know about climate science is from the movie An Inconvenient Truth and SciShow. I don't know if I've seen Inconvenient Truth. You've seen it?
That's been a long time.
It's been a minute.
Yeah, it's been a minute.
And then another question from Janet is, water levels in the Great Lakes are down 2 to 3 feet since 2020, according to U.S. Weather Service. Thank you for fact checking in real time.
Yeah, thank you, Janet.
Yeah. be getting a lot less precipitation. Or it's warmer and more evaporation,
Or both.
or both, probably.
Probably both. It's never just one thing. It's always some combination of multiple things.
Why do darker things get higher and colder things? So say if it's like a, a black car with leather seats, it's in the sun, but if it's cold, it's, more cold.
It actually is 100% dependent on the color of the material. Yeah, so
Why is that?
things that are dark in color
Yeah.
absorb all the visible wavelengths of light and reflect very little of that. Things that are light in color, like the whiteboard, this is reflecting most visible light. So things that are dark in color, not only are they absorbing the visible light, but they're also absorbing the infrared wavelengths that are responsible for heating them up. Yeah.
She'll get white cars with white upholstery. We don't have to burn our thighs.
I can't do that. There's be so much coffee and dog spilled in my
I
car
know.
so fast. The upholstery wouldn't be white for more than like 5 minutes.
Yeah.
No.
Janet, I had a follow-up to that. Does porosity affect the ability to absorb / reflect light?
Porosity will not. Porosity will deal with how much pore space is in a material. So it can influence how much it will heat up or cool down depending on what's in the pore space. So if you have like just say a rock with a bunch of pore space all full of air, air's got a fairly low heat capacity, the rock will heat up real quick. If you fill all that pore space with water, now you have 50% of the material or so full of a substance that has a really high heat capacity. So that will dampen the amount that it will heat up. That's actually a really fun experiment. Take like 2 pieces of pumice, take one, fill it with water, and then one don't, and see how they heat up.
Next science seminar demo. We'll make notes.
Or I'll just do it tomorrow, just 'cause I'm curious.
I sense more backyard science.
Oh yeah, absolutely.
So isn't it kind of like, you can't turn it around anymore? Like, really?
At this point, it's mitigate. It's reduce carbon consumption and emissions and mitigate.
Why does the weather change here? So, I mean, we sunny and then it 5 minutes later and it's back. Like, why does it do that here? We
Yeah.
have a lot of weather changes like in Colombia.
Yeah, it has to do with the particular air masses that are moving in off the Pacific. And especially if we're like transferring between a high pressure and a low pressure system. So like 2 days ago, Tuesday, I would have hated to give this talk inside. I had to go outside because it was, sunny and warm. And then Wednesday morning, what happened? It's what happens is a new weather system moves in, and depending on how much high pressure and how much low pressure there is, the pressure gradient between, if it's a broad gradient, like a long distance between the 2 weather systems, will have a very gradual change from one to the other. If they're really close, that means the air is going to be moving really fast from high pressure towards low pressure. And then the weather will change quickly. And along with really fast moving air, you get unstable air. So not only is it moving horizontally across the Earth's surface faster, it's also moving up into the atmosphere faster as well. And when you get things moving up into the atmosphere really fast, you get formation of storm clouds really quick. That's one way it can go from like, hey, it's nice and sunny, and then 2 minutes later, you're soaked. It's just you have an unstable atmosphere, which is forming lots of really kind of localized storm cells.
Are there any other questions from chat? From the Zoom folks? Janet also says Mount Rainier has more glacial ice than any other mountain in the US with 28 major glaciers. If these start to melt significantly, it poses a major concern.
There's more ice on this mountain than all the other Cascades combined. So yeah, that's the concern.
So how many more days of rain average will Seattle get?
She's planning her move out of Seattle.
Okay. For real, she said.
I don't know. It'll probably be the same. They'll just be more intense. Maybe less, but more intense. maybe more intense. One way to find out, and that's to go in the future, and we're doing that anyways.
Okay, awesome. Well, thank you, Dr. Selander.
Thanks,
for
everyone.
Sharing your science with us. Thank you those on Zoom for joining us. We appreciate it. And hopefully we'll see you next week. When I get to talk about genetically modified organisms. Thanks, everybody. Yeah.
I know.
45.
Just, I mean, if you could do it right now while you're here, that'd be great. Yeah.
Okay. If not, I'll do it tomorrow for you, okay?
Perfect.
Thank you so much. I appreciate you. 45. That is.
That was interesting, huh?
Body temperature is 30.
We'll see what we gonna run into now. Get outside, ooh, rain.
Yeah.
I was gonna say, in the basement, we have no idea what's happening out.
Okay, girl, I know.
Yeah.
We have to wait, get the
I- I-
elevator
I
and
think I'm
see,
there.
so we okay, we get to the turn.
Yeah.
You can feel it, right? Like if you're walking across a big parking lot and you're like, it's baking you from your shoes, melting the cold.
Should've grabbed the bag.
Yeah, so much for rubber soles, yeah.